All right, we're still in section 9.3 talking about significance tests for population means. I'm just going to backtrack to a couple examples previously here on this video. I don't think that on example 1 we had discussed part B here to this SIG test we did on testing whether the true mean length of these 6-inch subs was any different than 6 inches. We had went through the whole test. I believe at the end of the test, our conclusion that we had drawn was that we were going to reject the null hypothesis, and we said that we had convincing evidence that the true population mean length of 6-inch subs excuse me, is actually different than 6 inches. Okay, so we were rejecting the null hypothesis. Part B to this asked, given the conclusion that we made in part A, we rejected the null hypothesis, what kind of mistake could we have made, type 1 or type 2? We want to explain what that would mean in the context of this problem. So once again, our conclusion was that we chose to reject that the subs were 6 inches in favor of evidence showing they were not 6 inches. Okay, so we could say something like this. We could say that since we rejected the null hypothesis, okay, we could have made a type 1 error. Okay, a type 1 error is when you reject the null hypothesis, when in all reality the null hypothesis is actually true. So here's our context. We said that there was evidence that the subs were not 6 inches, when in all reality the subs would have been 6 inches. Okay, that's what a type 1 error would have been in this context. That we're kind of rejecting that the subs are 6 inches when in all actuality they are 6 inches. Excuse me. Okay, so we're going to pick up here with video B, which I believe that starts right here. We had talked a little bit about this in the last section, 9.2, where there was this connection where confidence intervals can be used in place of significance tests. Specifically, when we talked about proportions, we said those are slightly different, but they're really close, and so we can kind of tie the connection between, if something is a plausible value in a confidence interval, maybe that would be tied in with the conclusion that we're drawing for our significance test. But when we look at means, the confidence intervals and the SIG tests are exactly the same. Okay, there's no subtle difference here. So let me just talk a little bit here about a two-sided SIG test versus a one-sided SIG test and see if we can sort of see the connection between that and a one- and two-sided sort of a confidence interval here. Okay, so our two-sided SIG test, we know that's when we have a does not equal to. If we were to actually construct a confidence interval for a two-sided significance test, and I'm just going to draw a curve right here. Okay, now we're assuming that we're given, an alpha level of whatever that is. We're just going to call it alpha. Okay, when we are constructing these confidence intervals, this portion here in the middle would be just 1 minus alpha. That would be our confidence interval would span from here to here. Okay, and so we're saying split between these two tails. That would be like our rejection area where our p-value would be if we're talking about a two-sided SIG test. The alpha level would kind of be split between those two. Okay, so if we were talking about a 5% significance level, then we would be anticipating that our null hypothesis value would be located somewhere in the confidence interval. If it is, then we are not rejecting the null hypothesis. However, if it is not in that middle interval there, then that is when we would reject the null hypothesis in favor of the alternative. Now, it's slightly different when we look at a one-sided SIG test where we're either doing a greater than or a less than. So let me go ahead and just draw a curve here. Okay, if we're only talking about a one-sided test, okay, now we're just talking about like one side is shaded. Okay, again, when you're given the SIG level, the alpha level, that is all contained in that shaded area, and there's only one side that's shaded. But if I want to actually construct this so that it is a confidence interval, my confidence interval needs to be something spanning right here in the middle, okay? So if I'm going to block off alpha over there, I'm also going to need to block off alpha on this side so that this middle portion right in here, this confidence interval, would be found by essentially taking 1 minus 2 alpha. Okay, and you can see that demonstrated right here, that the null hypothesis would be located in that middle confidence interval span 1 minus 2 alpha. If it's there, we're not rejecting the null, and if it's not there, we are going to reject the null. Okay, so essentially, here's what our takeaway is on this. With proportions, the confidence intervals can only be constructed for two-sided tests, but with a mean, they can be constructed for both two-sided and one-sided. Okay, so just want to look at a small example here. I know that this concept is a little bit confusing. So suppose that we wanted to run a one-sample t-test for mu, and here's our null hypothesis, whatever mu is representing here, the population mean is 80. Okay, you can see here that the alternative is using a less than symbol, so that's denoting that this is a one-sided sig test, and they mention an alpha level of 0.02. Okay, now you can see all these 4 different confidence intervals that are constructed. Okay, technically, the one of those 4 that would align itself with a one-sided sig test of 0.02 would be something like this. Okay, I'm going to draw a small sketch here. Okay, so we would be housing all of alpha in this left tail because it's a less than, okay, and alpha was 0.02. Now if I'm going to try to construct, though, a confidence interval is centered right in the middle. Okay, so I'm going to block off this part and say this would also be 0.02. So essentially the confidence interval would be represented by 1 minus 2 alpha. Well, if I were to do 1 minus 2 times 0.02, that would leave me with 0.96, or a 95% confidence interval, would be the same thing as having done a one-sided sig test. Okay, so that's the one that would be most representative of this sig test that's defined here. Now, this question is actually asking us to kind of what conclusion would we draw for each of these different confidence intervals. So here's what you want to look for. Any of these confidence intervals that we have constructed, okay, we're looking for, does our hypothesized value, is it a plausible value in the confidence interval that's constructed? Well, we can see that for these first two, 80 is not actually included. So because it's not included, we would be rejecting the null hypothesis, and our reason is because 80 is not a plausible value. Okay, and I would basically make that exact same statement, so I'm just going to put some ditto marks here for the second one. Okay, now you can see for the third and fourth one, 80 is a plausible value in those confidence intervals. So since it's a plausible value, my conclusion would be, if I were doing a sig test representative of the same confidence interval, my conclusion should be that I would fail to reject the null hypothesis, and my reason is because 80 is a plausible value. Okay, and I'm just going to use ditto marks here because it would be the exact same conclusion for that confidence interval as well. So I think the big connection that you want to make sure that you have is whether you do a confidence interval or a sig test, they should always align with each other. You're rejecting your null hypothesis if your hypothesized value is not a plausible value in the confidence interval that you have created, and you're failing to reject your null hypothesis if it actually is a plausible value in your confidence interval. Okay, so we're going to take a look at a different type of study design. We would have studied different types of designs in Chapter 4. We talked about a matched pairs design where sometimes the same subject undergoes both treatments, or you see this a lot with twins where maybe they will pair up and have one twin do one treatment and the other twin will do the other treatment, and they kind of compare the two. So Anytime you have a study design and you're making either two observations on the exact same individual, or you're making one observation on each of two similar individuals, we call that data paired data. And it essentially comes from that matched pairs design that I was referencing. Okay? Now, paired data is usually analyzed as a single sample. So even though we're going to call this a paired t-test, it is really the same thing as a one sample t-test. Okay, not really any different in terms of how we're going to go about constructing this. Apart from just getting the initial set of data, we need to set up and find the differences between the two sets of data we have, or the two observations. Okay, and again, this is called a paired t-test, which essentially is going to be executed the same way that a one sample t-test is. Okay, now here is the difference though. You are always going to have your null hypothesis represent what the average difference is between the two observations. So notice that I have mu sub d. And our null hypothesis is always a statement of equality, meaning there is no difference at all between the two things you're comparing. And that is why this is always going to be a 0. Okay. Your alternative, it depends on whether we're talking about less than, greater than, or not equal to 0. Okay. And then you'll notice here, we have set up, this is our average difference between the two, and this is the standard deviation of the differences. Okay, the one thing that I want you to make a note of, though, is this should always be a 0. Okay, always use 0 there, and that's because our null hypothesis is always going to be a statement of there is no difference between the two things. So that is always a 0. That's what typically goes here is the mu sub 0. Okay, these are t-test problems, so we're always needing to report what our degrees of freedom are. So let's try an example like this. It says, is the express lane faster? Well, for their second semester project in AP Stats, Libby and Catherine decided to investigate which line was faster in the supermarket. Was it the express lane or is it the regular lane? So to collect their data, they randomly selected 15 times. I'm just going to make a note of that because I know that's going to be one of my conditions here. Okay, they randomly selected 15 times during a week, and they went to the same store. They bought the exact same item. One of the students used the express lane, and the other used the closest regular lane. Now, to decide which lane each of them would use, they flipped a coin. Okay? They entered the lanes at the exact same time. They paid with the exact same method. This is all what we call control in the design of an experiment here. Okay, trying to make everything the same except the treatment itself, which would be the two different lanes they're entering. And they recorded the time in seconds that it took them to complete the transaction. The question here is they're asking us to carry out a test to see if there is convincing evidence that the express lane is faster on average. All right, so we're going to let a capital R represent the regular lane. If you want to label the first column here, this is the time in seconds that it took for each of the 15 different times that they did this. And we're going to let an E represent the length of time in seconds it took them to complete their transaction in the express lane. Okay, now we're really wanting to compare the two of these, and so what we're after is we don't want these two different sets of data. We want to find what is the difference between these. Okay, is the express lane faster than the regular lane? So our parameter is not just mu, but it's mu sub d. Okay, and this represents the true population mean difference. Okay, very important that we're talking about the differences in checkout times. Okay, and anytime you're subtracting something, you should kind of define the order of subtraction. So I'm going to go ahead and just define the order of subtraction as being the regular lane minus the express lane. Okay, so I'm going to go ahead over here and define this column as regular minus express, and you can see this would be the difference in those two times. Okay, and I already have those filled in here. These are the difference in seconds. So anytime you're seeing a positive value here, that means that the regular lane took much longer than the express lane. Anytime you're seeing a negative number here for the difference, in fact, the express lane appeared to be longer than the regular lane. Okay. All right, let's go ahead and draft our hypotheses here. Okay, the null hypothesis is going to be that there is no difference at all. Now we need to be careful with this. The alternative hypothesis, now what we're looking for is we're trying to figure out, is the express lane faster? Okay, is it faster? Well, if this is faster, then we expect these times to be smaller than these times. So remember the order that we're subtracting in regular minus express. So we're wanting to show that that difference would be greater than 0. Okay, because if these numbers are larger than these numbers, then the differences would be all positive. Okay, this is also where we cite what our alpha level is, 0.05. Okay, and then we're going to go through our assumptions or our conditions here. Okay, the first one, we're going to say there were 15 random times selected. Okay, the second one is our 10% condition. 10 times 15 is 150. That's less than or equal to all the times, okay, that they could have come and checked something out. Okay, and now we need to check off that normality condition here. Okay, well, our sample size was only 15, so we can't use the central limit theorem. There's no mention that the population distribution is normal. So what we would end up doing, okay, what you're going to do is you're going to take all of these difference values. Those are all going to be placed into L1 on your calculator. Okay, you're going to make a box and whisker plot, and you're going to graph it on your paper. Okay, I'm going to label my x-axis is the difference in lane times. Okay, just give a rough scale here just to kind of count by. And I'm going to go ahead and just draw a very rough sketch of this box and whisker plot. Okay, but really, you really need to be labeling your x-axis, okay, what that represents. Now, it does feel like there is a little bit of a right skew here because that is longer, okay, but I'm going to go ahead and make a statement that there's no extreme skewness, or there's no outliers. If I would have seen an outlier on my calculator, it would have been denoted by like an extra dot off to the side there, and I didn't see anything like that. Okay, so that means I can conclude, therefore, it is approximately normal. Okay, now I'm going to say the name of the test. Okay, this is called a paired t-test for means. Paired t-test for means. Okay, paired because I'm pairing up these two sets of data to create a single set of data, and this is what I'm focusing on, the single set of data here. Okay, now for me to get the t-score, okay, since I have the set of data, you're going to go back. Remember, we put all that data in L1. Okay, so we need a little bit of information here. Okay, our formula is going to be, what goes here is our sample mean, and what goes here is our hypothesized mean. Okay, well, we know the hypothesized mean is always going to be a 0. The sample mean needs to come from me running one variable stats on my calculator. Okay, we did this on the previous video, I believe. You're going to press the stat button, you're going to go to the calculate menu, and you're going to pick option 1 variable stats. Okay, when you choose that, it should tell you that the sample mean time here is 42.67. The other thing you're going to want to grab from that screen is what the sample standard deviation is. We need to use that down here in our formula, and that is, over the square root of your sample size, which is 15. Okay, this comes out to a t-score of 1.97. We then would draw a rough sketch of a bell-shaped curve. Okay, keep in mind this was a one-sided test, a greater than. So I'm going to put 1.97 here. I'm shading to the right. I'm going to be doing TCDF to get my p-value here. I need lower bound, upper bound, degrees of freedom. Lower bound 1.97, upper bound 10,000. Degrees of freedom, remember that is sample size minus 1. That's going to be 14. And my p-value is 0.0347. Okay, so now I can compare. I'm going to say since the p-value of 0.0347 is less than the alpha level of 0.05, our decision is we are going to reject the null hypothesis. Okay, when we reject, that's when we have convincing evidence. So we're going to say we have convincing evidence that, and now I'm going to look back at what did we say our alternative hypothesis was. That's what our evidence is in favor of. Okay, it's showing that the true mean difference, you can just look up here at what we defined m sub d, or mu sub d to be, rather. Okay, so we have convincing evidence that the true population mean difference in lane times is greater than 0. And I'm just going to, again, just for clarification here, to denote what the order of subtraction is, regular lane minus express lane there. Okay, that is called a paired t-test, here. Okay, we're going to wrap this up with this final example, which is also looking at paired data here. Don't know that we'll do the entire thing. There's just a couple of things on this that I just want to highlight for you. Most of the problems that we've done up to this point have all been samples that have been taken. They've randomly selected things to get their sample. You can also do significance tests from experiments. Okay, now we know when you do an experiment, most of the time the individuals that you're using have not been selected at random. They're generally volunteers. Okay, however, we know the randomization comes in because when we assign the treatments to the individuals, we do that randomly. Okay, so there's a couple of things that this is going to affect with our conditions, and I want to be able to address those. We might not do this whole entire problem here, but we want to just do the first few parts so that you see the difference here when it's an experiment versus when you've just gathered people randomly from a sample. It says researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Now, during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. Now, here's where we see the order in which the subjects took the caffeine and the placebo was randomized. So at the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. Okay, so if we're looking for would there be an increase in depression, okay, we want to keep that in mind. That'll be important when we're trying to draft our alternative hypothesis. It says a higher value equals a higher level of depression. Okay, so let's look first of all at the P, the parameter, and you can see the data that we have here in this table is we have essentially the first column, I'm going to call that C. Okay, these are marking off what the levels of depression were for the people who were given the caffeine pills. Okay, and then the levels of depression for the people who were just given the placebo pill. And then notice in the third column, these are our differences, and they did placebo minus caffeine. So be very careful with that. It's actually this column minus that column. Okay, so I'm going to go ahead and just kind of highlight that column because this is the set of data that we're interested in. We're interested in the differences between placebo and caffeine pill. Okay, so we're going to define our parameter of interest, not to be mu, but to be mu sub d, which is the true population mean, keyword here, difference. Okay, difference in depression levels. Okay, we're measuring the difference in depression levels, and I'm going to go ahead and denote the order of the subtraction. It is placebo minus caffeine. Okay, placebo minus caffeine. Now, our alternative hypothesis is that there's no difference between the depression levels, whether you took the caffeine pill or the placebo pill. Okay, so that's always 0. Now, here's where we have to be careful. Now, here we want to know, keep in mind, it said here, those who were deprived of caffeine, would that lead to an increase in depression? Well, let's look at these numbers over here. If you're deprived of the caffeine, okay, then we're looking at, are these, because we're doing placebo minus caffeine. Okay. If that's the case, then we're talking about this difference would be greater than 0. Okay, greater than 0, because the placebo means you were deprived of the caffeine. So we would expect these numbers to have higher depression rates than when you're given the caffeine pill. So placebo minus caffeine, these would be positive numbers if it resulted in an increase in depression if you were deprived of the caffeine. Okay? All right, and then we're just going to look at the conditions for this, and we probably won't finish the rest of this problem here. Normally here we would note that it mentioned that the people were selected at random. But since this is an experiment, you just need to make a reference that it said that the treatments were randomly assigned. Okay, treatments were randomly assigned. So you just need to make that statement, and that would check off the random condition. Now, the 10% condition, this is interesting. The 10% condition only applies if you're gathering a sample, because we want to make sure that our sample size is small enough that if we took 10 times our sample size, it's going to be less than or equal to the population size. If it's an experiment, then it is not necessary for you to show anything with the 10% condition. So I'm just going to make a note here, no 10% condition because this is an experiment. Now, you don't have to say this on the AP test. I'm just writing this here so that when you look back at this problem, you understand why we didn't actually check off or check the 10% condition, but you could just skip over that condition if it's an experiment. Okay. Now we do still have to check the normal condition. Okay, and here again is where you would take all this data that is in your L1, you would make a box plot. Again, you would show that box plot. This is the difference in depression levels. And I'm just going to mark off here just some nice labels so that we have them to kind of sketch this a little bit here. All right. So our box plot maybe roughly looks something like this. Okay. And we just want to make a note that there is no extreme skewness or outliers. Therefore, it is approximately normal. Okay, and then we would continue on with the problem. This would be considered a paired t-test, and we would probably need to do the one variable stat again in order to draft our t-value, etc. Okay, but the main thing was you acknowledging that if it's an experiment, you have to just say the treatments were randomly assigned, and you'd completely pass over that 10% condition. Okay, I believe there are a few problems listed here at the bottom that you could go ahead and try that go along with this video.